welcome to episode 4 of Doing Research in Psychology Advanced. So, a quick recap. Last week, if you'll remember, we were developing intuitions about randomness, what it looks like, and how we can distinguish genuine pattern from pure noise in our datasets. So we learned about for instance, the random generating process and the law of large numbers. That chance can be lumpy, that in the short run we can get long strings of sequences in a row just due to chance. It looks systematic, but if we were to take a larger sample in the long run, it can even out. And we often mistake this streakiness, this lumpiness, for pattern, a genuine pattern in the world. That a streak of heads when flipping a coin, or several reds in a row on a roulette wheel, or a string of cancer hotspots in small towns, or too many repeats of the same song on our Apple playlist, are indicative of some sort of patterning that we can predict ahead of time from a small sample of data. But we can often be fooled by small samples of data. We also learned about regression to the mean, so this idea that if we have one score that's in the extreme of distribution, so whether that's above or below the mean, the next score that we sample from that distribution is likely to be closer to the mean. So a great example of this is swimming race times, for instance. If you perform extremely well or extremely poorly on one particular race, your next race is likely to regress to your mean performance. It's the same with quizzes and how you perform in a job interview and a whole range of other scenarios where you only have one or two observations. And we also revisited ideas about experimental design, so distinguishing between within subjects design, where we're comparing apples to apples, so you have the same participants participating in every single condition in your experiment, and between subjects designs, where we're comparing apples with oranges, so you have a different sample of participants who are participating or randomly assigned to different conditions in your experiment. And so using a between subjects design typically introduces more sort of random error variance just due to individual differences between your samples. Whereas within subjects designs rules that particular chance explanation out. So it's a more powerful design from the perspective of ruling out possible chance explanations for our data. And then we finish by looking at how we can estimate or measure differences between two means. So whether we're looking at independent samples in a between subjects experimental design, or paired samples as in within subjects design. Right. So the statistical tests that we use to distinguish between pure chance explanations and systematic explanations for our data really depend on the experimental design that we've used. And there are a whole bunch of assumptions that go along with these tests. We really only scratched the surface last week in looking at how we can estimate differences. Right? So this week we're going to be looking at more measuring differences. So in the first section there, we'll be looking at comparing variables that have more than two different means. In the second section, we'll expand on that even further, looking at how we can compare means across two different variables. And finally, after our foray into measuring differences across more than two group means and more than two variables, we'll transition into interpreting p-values and critically evaluating the merits of using p-values as an indicator of the magnitude of a relationship or an effect. Now, we might save this over until episode 5, so next week, but just to foreshadow where we're heading after this next section on measuring differences. Okay, so kicking off with measuring differences. So last week, we talked about scenarios where we might want to compare a single mean to a constant value, and a good example of that is where we're interested to know whether or not performance on some task or measure is significantly better than chance, where chance is a constant of a probability of responding correctly of 0.5 in an experiment, for instance. We also covered the different sorts of statistical tools we have available to us when we want to compare two different means. And so those could be two different means of two different independent samples of observations, where we say, for instance, have a group of experts and novices who are performing a particular task, and we want to know whether those two groups, our apples and oranges, differ in a meaningful way from each other. But we also might compare two means where we have matched samples of data. So two samples of data that are paired or matched in some way. So within subjects designs are a good example of that, where each participant contributes an observation in every single condition. And we put all of this together in our R notebook, where we ran through various different ways in which we can plot our data when there are two means, and ways in which we can run these statistical tests in R, all in one neatly contained data analysis script that's entirely reproducible. So if I was to download your R notebook, I should be able to reproduce the exact results that you get on your end when you're running the notebook on your machine with your version of RStudio. Right, so many of those tests that we covered last week you may already be familiar with from second year statistics. But what if we encounter a situation, which is fairly common in psychology, where we have more than two group means? Right, well, we, for instance, might have a variable where we have more than two groups. We might have novices and trainees and experts, for instance, in an experiment on expertise in a particular domain. What do we do in scenarios like this? How can we probe for meaningful differences in our data when we have more than two levels in our variables of interest? So handily, R has a few different data sets built in that we can draw on to illustrate these different designs and ways in which we can estimate and measure differences between various different kinds of data sets. So this one, for instance, is the ToothGrowth data set in R. So it contains the results of an experiment studying the effects of vitamin C on tooth growth of 60 guinea pigs. Right, so each one of these dots in our dot plot here is actually a different guinea pig. And so each animal receives one of three levels of vitamin C, 0.5, 1, or 2 milligrams per day. So we know we're dealing with a between subjects design because each guinea pig only receives one dose level in the experiment. They don't receive all of the different dose levels. Then over here we have a dot plot of the same data where the black line in the middle represents the median for that particular group of observations for that particular dosage level. And the interquartile range. So any data points that fall outside of this range are considered statistical outliers. So the box plots are particularly useful for spotting impossible scores or observations and extreme outliers in our data. And then down here we have a histogram of the same data set as well, of the three different dosage levels in orange, yellow, and green. And these are overlaid with smooth density plots as well. So these in particular are handy for getting a sense of whether or not, or of the distributional nature of our data. Are we dealing with a whole lot of skew? Do we have a really long tail in one direction or the other? Are our distributions really skinny or really fat? And is the variance across the different levels of our variables of interest roughly the same? So are the data roughly normally distributed across each of the levels of dosage? And is the variance across each of these levels roughly similar? Those are the sorts of assumptions we're making when we run parametric tests, and so different visualizations like this are particularly handy for developing intuitions about whether or not the tests that we're planning to run are appropriate for the data that we're dealing with. Okay, so having said that, let's get stuck into doing a bit of data analysis. So in a design like this where we're dealing with one independent variable, so dosage of vitamin C, and our dependent variable of tooth growth, we'd be looking to run a one-way analysis of variance. So remember that our observations here are independent of one another. So this guinea pig over here is different from this guinea pig over here, is different from this guinea pig over here. And they've been randomly assigned to these different conditions, so we can assume that there's independence between the observations in these different conditions. So in this sort of scenario, we are in particular looking to run an independent samples one-way analysis of variance. And as with all parametric tests, they come with a bunch of assumptions. You've seen some of these before. So one of the assumptions, for instance, is that the dependent measure or variable is on a continuous scale, so an interval or a ratio scale, that the dataset contain two or more categorical independent groups, that the observations are independent, that we have no extreme outliers, and that we have approximately normal distributions for each category of the independent variable. And finally, you've seen this one before with the between subjects t-test, we're assuming homogeneity of variances. This is also known as equality of variances. So what we're looking at here is whether or not the distributions of each level of our independent variable are roughly the same shape, that they have the same variance across, similar variance across each of those levels of our dataset. So the box plots are useful for identifying or probing that outlier assumption. The density plots or histograms are useful for probing whether or not we meet the normality assumption, and also the homogeneity of variances assumption. And the dot plots are sort of the best of both worlds, but without the redundancy. So the raw data points, the guinea pigs themselves, are organized to represent the distributional nature of the data. We have that overlaid with a box plot here, and then we simply overlay the box plot to identify any particular outliers that we might want to look into a little bit further. So a handy package to know about when we're running an analysis of variance in R is the EZ package. Right, so here we're calling the as ANOVA function within the EZ package. Here we're specifying the data that we're calling on, the dependent variable, so in this case ToothGrowth, the participant variable, so guinea pig, and the between subjects variable, which is dose of vitamin C. And when we run the analysis on this particular dataset, the output should pop up right beneath the code chunk. So here we have the output for our one-way analysis of variance. Right, so here we have our degrees of freedom. So we know we have 3 levels of dosage. So 3 minus 1 is 2. That gives us our degrees of freedom. We have 60 participants minus our 3 levels of dosage, so 57. Our F statistic, and our raw exact p-value in scientific notation. And over here we have generalized eta squared as a measure of effect size. So it tells us this is a measure of magnitude that gives us an indication of how big this effect is, overall effect is, between these 3 different levels of dosage. So the reason why the EZ package is a really handy one to know about is because it gives us generalized eta squared, which is a particularly handy estimate of effect size to report because it allows meta-researchers to compare effect sizes across studies using different designs. Also in our output, we have the results of a Levene's test. So this is a test we use to probe whether or not our data meet the homogeneity of variance assumption. Right, so one rule of thumb is if the p-value of the Levene's test is less than 0.05, our assumption of equal variances is violated. That our samples of observations come from 2 different distributions with different variances. So one of the interesting things about analysis of variance is it's what we call an omnibus test. So we might find a significant effect of dosage of vitamin C on tooth growth overall, but we don't know where those meaningful differences lie, right? So we don't know if the difference between the 0.5 milligram and 1 milligram dosage is meaningful, or whether this difference between the 1 and 2 milligram dosage is meaningful, or indeed whether the 2 and the 0.5 milligram dosage is meaningful. But what we do know is that we have a significant main effect of dosage of vitamin C. So there are differences somewhere, we just don't know how to characterize those differences. So to do that, to make a comparison between 2 different levels of our overall factor of dosage of vitamin C, we need to set planned contrasts ahead of time before we've collected any data. So contrasts allow us to test simple effects within our design, so by comparing 2 different levels of our dosage factor, for instance. Now, depending on our predictions and our research question, there are different kinds of contrasts we can set. And the simplest kind is the treatment contrast. So this is where we have one level that's considered to be special, that acts like a baseline category of sorts. So these kinds of contrasts are common in randomized control trials, where you might be comparing a treatment condition to a placebo and a control condition, for instance. Now, treatment contrasts are useful in a lot of situations, especially in clinical and educational research, where we're comparing various different interventions to a baseline. But it really only makes sense to use this kind of contrast, treatment contrasts, when we're dealing with a true baseline category. In other situations, however, sometimes you don't really have a baseline level of your particular variable of interest. And in cases like that, it may make more sense to compare each group to the mean of all of the other groups. So this is where helmet contrasts can be useful. So these involve comparing each group to the mean of the previous levels in your variable. So that is, the first contrast represents the difference between group 1 and group 2. The second represents the difference between group 3 and the means of group 1 and 2, and so on. Right, so these might be useful in situations where we're interested in additive effects, where we're sort of incrementally increasing dosage of vitamin C, for instance. And a third kind of contrast we might want to run, depending on our design, is what we call the sum to zero contrast. Right, so we use these to construct pairwise comparisons between groups. Specifically, each contrast encodes the difference between one of the groups and a baseline category. Right, so you might have a scenario where you don't necessarily have a control or a placebo condition per se, but you have one particular level of your variable that you're interested in comparing each other level of your variable to. And with each of these contrast methods, we're implicitly assuming that the different levels of our independent variable of interest are discrete or qualitative in some sense. Like, for instance, we might be comparing happiness levels across South Australia, Western Australia, New South Wales, Queensland, and Tasmania, for instance. Right? So there's no principled order to each of the different levels of our variable of interest, which would be state in that particular case. Right? So these sorts of contrasts are particularly handy when we're dealing with unordered or discrete independent variables. Right, but sometimes our independent variables do have an order to them, like dosage of vitamin C, for instance. And so in these kind of cases, when we're dealing with an independent variable that's ordered as opposed to discrete, we have another option available to us in describing differences across more than two group means. That is, we have polynomial contrasts. So these are a special set of orthogonal contrasts that test polynomial patterns in our data with more than two means. So essentially, we're describing the trend across the different levels of our independent variable of interest. Are we dealing with a linear trend, a linear increase in tooth growth with increases in dosage of vitamin C? Is it quadratic? Does it have a bend in it? Right, so essentially what we're trying to capture with polynomial contrasts is the overall trend across the different levels of our independent variable. Right, so we call this particular form of analysis a trend analysis. Right, so trend analyses, along with other forms of contrasts, are really a method for further articulating the results that we're dealing with, further articulating or specifying the pattern of data that we're observing. It allows us to transform our omnibus blob of a significant effect into something that's a little bit more informative and descriptive of the differences between each level of our variable of interest. So there are three main kinds of trends we might see in our data, particularly in psychology research. The simplest is the linear trend. So if we get a significant linear trend across the different levels of our independent variable, then we're dealing with data that doesn't have any bends in it. That each increase in our dependent variable with our independent variable is roughly the same. Another kind of trend that we might see is what we describe as a quadratic trend. So here we're dealing with a bend in our data across the different levels of our independent variable. And the third, less common kind of trend that we might see is what's called a cubic trend. So here we're looking for not just one bend, but at least 2 bends in our data. So we can see here with our ToothGrowth dataset that our results probably map fairly closely onto a quadratic trend. But let's test it out and have a look. Right, so for polynomial contrasts, we'd run our one-way analysis of variance as usual using the ANOVA function within the easy package. And then we need to go through a few steps to construct our polynomial contrasts. So the first thing we need to do is set our vitamin C dosage variable as an ordered factor. So that's what this line of code here is doing. And the second thing we want to do is select the options for our contrasts. So the first option here is treatment contrasts, and these would be run if our factor was discrete, or if ordered was set to false. But notice our second option here is set to contra-poly, which is shorthand for polynomial contrasts. And this is the contrasts that we want, and it'll run if we set our factor to ordered equals true. So we've selected our contrast options, we've set our dosage factor to ordered. The third thing we want to do is set our contrasts. So here we're specifying that we have 3 different levels of our dosage factor and the 3 different levels of that particular factor. And then finally, we simply fit a linear model specifying our contrast. So notice here we've selected the contrast we want to run for dose as contrast poly, which was set in the previous line. So then we click run, and this is what the output looks like. Right, so dose.l indicates a linear trend, and we can see here we have a significant linear trend. So as vitamin C dosage increases, we get a linear increase in tooth growth. And we also have a significant quadratic trend as well. So those are polynomial contrasts, and they're useful for a range of different scenarios where we're dealing with an independent variable that has an order to it. But let's run through one more use case of setting contrasts. Let's take the PlantGrowth dataset in R's datasets to illustrate what it can look like to run treatment contrasts. So again, whenever we're running contrasts, we want to set these ahead of time before we've collected any data. And remember, the treatment contrasts are where we have one level that's sort of special, like a placebo or a control condition, and we're comparing our other levels to that special baseline condition. So with this particular dataset, we have the results from a plant experiment that compares the yields as measured by the dried weight of the plants obtained under different conditions. So we have a control condition and 2 different treatment conditions. And again, here we're dealing with a between subjects design, so each one of these dots in our dot plot is a different plant. And then we have our density plots and our histograms and our box plots to the right here to get a feel for whether or not we're dealing with anything that we should be suspicious of, any extreme outliers or impossible scores, or extremely skewed data, or vastly different variances across our different conditions. So to run the treatment contrasts with this particular dataset, we'd run our ANOVA as before, except for now we've got the weight of plants as our dependent variable, the ID of the plant as the participant variable, and we're specifying a between subjects variable as group. So whether or not the plant was randomly assigned to the control or one of the 2 different treatment conditions. And here's how we set our treatment contrasts. So again, we want to set or specify the nature of our factor using the factor function. So we're outlining the 3 different levels of our variable group within our dataset. And we're saying that these levels don't have an order to them, that they're discrete. So we're setting ordered to false. We selecting the contrast options that we want. Thirdly, we set our contrasts. So we're putting control, treatment 1 and treatment 2 into contrast treatment. And then we fit a simple linear model specifying those contrasts. And here we have the output. So here, group treatment 1 is the contrast between our control condition and our treatment 1 condition. We can actually see that there's no significant difference between those two groups. The second contrast here, group treatment 2, is the contrast or the comparison between our control condition and our treatment 2 condition. And again, we can see here, we also don't have a significant result. The p-value is greater than 0.05. So even though it looks like there's some differences between those three groups, when you actually compare each of the treatments to the control, it's possible that those differences could be simply due to chance. So we'd be retaining the null hypothesis in this particular case. And finally, what if we're dealing with a situation where we don't have independent samples of data, but in fact our data are paired? What if we're dealing with a within subjects experimental design? So to illustrate, I'm drawing on here the Morley dataset, which we can access with base R, so we don't need to import any data to plot and play around with this particular dataset. So here we have experiment as our independent variable and speed of light as our dependent variable. And so there are paired observations across each of the 5 experiments that were run in this particular dataset. So again, we can represent our data with box plots, except in this case, we've overlaid those box plots on top of the raw data points across each of the levels of our independent variable. So this is particularly useful when we're dealing with paired data because we can connect the dots. We can see how our paired data move up and down across the different levels of our independent variable. And we can also represent the same data with our dot plots and also our histograms and density plots on the right here. So again, getting a sense of the distributional nature of our data and whether or not we're dealing with any particularly worrisome outliers in our data, in our sample. Right, so here we have more than 2 group means, but we're also dealing with paired data. So what tests can we run? Well, we can run a one-way analysis of variance, but for paired observations. So the assumptions are similar here, but there are a few slight and important differences. So we still have the assumption that the dependent variable is on a continuous scale, that we have 2 or more categorical groups or conditions within our experiment. In this case, we're assuming that the observations are paired or matched, that there are no extreme outliers, that we're dealing with approximately normal distributions for each condition of the independent or level of the independent variable. And the one that's particular to repeated measures designs is the assumption of sphericity. So this is assuming that the variance of the population of different scores for any 2 conditions should be the same as the variance of the population difference scores for any other 2 conditions. So simply put, this is sort of like the repeated measures equivalent of the homogeneity of variance assumption. When we have 2 paired observations and we take the difference between those 2 observations, we want to make sure that those different scores are roughly of the similar variances across each of our conditions. So this assumption can be particularly worrisome in within subjects designs because if it's violated, it can increase the probability of getting a type 1 error. But thankfully, there's a very easy test we can apply and a correction we can apply if our data do happen to violate this particular assumption. And I'll show you how to spot that in your data here. So with a paired one-way analysis of variance, the data analysis is straightforward. It's very similar to the independent samples example. So using the ANOVA function, we specify our data, our dependent variable of interest, which is speed of light in this case, our participant variable, which is run in this particular case, in this data set. And here, notice this has been changed from between to within. So we're specifying a within subjects variable in our data set, which is experiment. Right? So we run our ANOVA. We find we have a significant effect of experiment. So remember, we have 5 levels of our factor. So our degrees of freedom is 5 minus 1, which is 4. We have our F statistic, our p-value, and an indication of whether or not that p-value is less than 0.05. So that's a conventional cutoff for rejecting the null hypothesis. And we have our generalized error squared as an indicator of the size of that effect. But again, we don't know where the differences lie. We just know that there's something going on with the experiment. We need to do a little bit more digging with some planned contrast to find out where exactly the differences lie and what the nature of this pattern of results across the different experiments really is. And in particular, to check that our data don't violate the assumption of sphericity, we want to run a Morley's test. And so thankfully, this comes along with the output from our analysis of variance with the ANOVA function. And it'll look a little something like this. So we'll have a W statistic, a p-value, and an indication of whether that p-value is less than 0.05. And now with Morley's, if our p-value is less than 0.05, then we'd infer that we've violated this assumption of sphericity, and we want to be cautious in interpreting this significant main effect of experiment on speed of light. And so if we do get a significant Morley's test, there are a few different corrections we can apply to our p-value. So rather than reporting the raw p-value of our main effect, we'd pick one of these different corrections. So we have the Greenhouse-Geyser correction and the Heinfeld correction. The Greenhouse-Geyser correction is slightly more conservative. So many people choose to report the Greenhouse-Geyser correction in cases where sphericity has been violated, erring on the side of caution, erring on the side of not wanting to make a type 1 error or reporting a false positive result in their research. So in cases where sphericity has been violated, it's not the end of the world. We can apply a rather conservative correction to our p-value to make sure that we're not artificially inflating our results. Okay, so we've stepped through a few different use cases between subjects and within subjects use cases where we're comparing more than two group means. So have a go at putting this into practice. See if you can describe an experiment where you'd use an independent samples analysis of variance versus a paired samples analysis of variance, mapping onto the things that we covered last week around experimental design. Remember, we want to pick the right tests for the data, and so it's useful to think about how the research design side of things connects up with the statistical analysis sides of things. Next, I wanted to briefly touch on scenarios where we're not just dealing with one variable, independent variable. Next, I wanted to briefly touch on scenarios where we're not just dealing with one variable, but more than one independent variable. So we've dealt a lot with cases where we're comparing two different means or more than two different means across one particular factor. So group or dosage of vitamin C or treatment. But it's common in psychology to ask research questions that are really more about how different variables interact. How do different variables A affect our dependent variable relative to different levels of B? Right, so cases like this where we're comparing two group means, or two samples of paired observations in this case, we're dealing with a design that has just a single variable and two different levels of that variable. So this is an experiment that my honours student ran this year looking at the effect of visual crowding. So if you can remember, this is a phenomenon where if you present something in someone's peripheral vision, it's much more difficult to recognize it if it's surrounded by clutter, by other items in your periphery, as opposed to if it's just presented in isolation. But in this particular project, we were looking at whether or not we could release an object from crowding, whether we could minimize that crowding effect by changing the kind of clutter that we surround an object with. In this case, objects that are of the same kind as the one you're trying to find. Right, so this is what we call a 2x2 within subjects design. And it's a 2x2 because we have two variables, crowding and congruency, and two different levels to each of those variables. So within the crowding variable, we have the objects presented in your periphery are crowded or uncrowded, so two different levels of crowding. And then with the congruency variable, we have flanking objects that are either the same kind as the target or a different kind to the target. So 2 different levels of the congruency factor. So we see we have 2 variables that each have 2 different levels. And it's a fully within subjects design because every participant contributes an observation to each of the 2 levels of each of the 2 variables. And so essentially what we wanted to know is if this classic visual crowding effect, where perception and recognition is much poorer when an object is surrounded by a clutter, can be reduced by surrounding an object with other objects of the same kind. So we wanted to know if this difference here was different to this difference here, right? Right, so the details aside, this sort of scenario where we're interested in interaction between 2 different variables is very common in experimental research in psychology. Most of the time we're interested in how different variables interact, and therefore we are often dealing with research designs that use more than one variable. Right, so how do we deal with the data set where we have more than 2 variables, as in this example here? Well, it's a small extension on running the one-way analysis of variance. So here we're using the easy package again for the easy ANOVA function. We specify our data, our dependent variable, which is mean proportion correct, our participant variable, and because we're dealing with a fully within subjects design, we use the within element instead of between, and because we have 2 different variables, we indicate that in our model. So here our 2 different variables are crowding and congruency, or congruent as it's specified in the dataset. And here we have the output of our analysis of variance. So we have a main effect of crowding, so collapsing across levels of congruency. So just looking at the overall difference between in proportion correct for objects that are crowded in our periphery and presented in isolation, is there a meaningful difference between those 2 groups? And it appears that there is. We have our generalized effect size over here for our main effect of crowding. Here we have our main effect of congruency. So collapsing over our crowding variable, is there a significant difference in mean proportion correct for our congruent condition versus our incongruent condition? And indeed, we have a significant main effect of congruency as well, with a slightly smaller effect size there. And finally, we have the interaction term. So is there a significant interaction between crowding and congruency? In other words, is this difference over here different to this difference over here? Do we get a bigger effect of crowding over here and a smaller effect of crowding over here? And indeed, it looks like we do. There's a significant interaction between crowding and congruency. So whenever we find a significant interaction, we want to take care in interpreting the main effects because they can be misleading. And we have more information to go by. And we have the added information of the interaction. So we know that performance is worse when objects are crowded in our periphery, but that crowding effect is bigger when the flanking objects are incongruent with the target, as opposed to when they're congruent with the target. So you notice whenever you describe an interaction, there's a but. We have this crowding effect, but it's smaller over here than it is over here. We have an effect, but it's different in this condition than it is in this condition. Right? So whenever we have a significant interaction, it's always best to interpret our data at the level of the interaction. And handily, because we only have 2 levels of each of our variables, we don't need to worry about setting contrasts and running contrasts because we know where the differences lie. There's only 2 levels of crowding, and so we know if we get an main effect of crowding, that the difference is between our 2 different crowding conditions, and vice versa for congruency in our interaction term. So the handy thing about bifurcating the world and using variables that have just two factors is that it makes the interpretation much simpler. It's much easier to interpret 2x2 designs than a 2x8 design, for instance. And so we'll delve a little bit more into interpreting interactions and designing experiments in a parsimonious way so that they're easy to interpret and describe a little bit later in the course. And also included here is just another way of running the exact same analysis in R using R's AOV function. So for this, we don't need to load the easy package. It's already baked into R, and it's just a slightly different way of running a within subjects ANOVA. So we specify our dependent variable here, our two independent variables, and also an error term. Now, typically, this is estimating the sort of random error variance due to the participants in our experiments. But because we're using a within subjects design, we can actually partial out the variance attributed to participants for each of our within subjects variables. And with this expression of ANOVA, we specify our data frame at the end here. So that's within, but let's say had we manipulated those two variables, so crowding and congruency, in a between subjects design where every participant is randomly assigned to only one crowding condition and one congruency condition, then we can run a between subjects analysis of variance. So we're specifying our two variables as a between subjects variable instead. And here's the expression with the AOV function. So we can't partial out any of our error variance due to participants because we're dealing with a fully between subjects design in this case. So we need to account for the sort of error variance that might be introduced simply by random differences between individuals that have been assigned to different conditions in our experiment. Remember, in this case, we'd be comparing apples and oranges as opposed to apples with apples. And so we need to account for the sort of random error variance that can creep in when we opt for a between subjects design. And another option that is more common than you might think is a mixed design. So it might not be feasible, for instance, to run all of your variables as a within subjects factor, but you might still be able to run one of your variables as a within subjects factor while the other is between. So whenever you're dealing with the design where you have multiple variables and some are within and some are between, then we call that a mixed design. And we can use the same methods for running an analysis of variance for a mixed design. So with the as ANOVA function, we specify our data, our dependent variable, which is mean proportion correct, our participant variable. We separate out our within and between factors. So we specify our within factor, let's say it's crowding in this particular case, and a between subjects factor, let's say it's congruency in this case. And again, we can run the same analysis with the AOV function. So this time, only partialing out the variance due to our within subject factor of crowding. Congruency is a between subjects factor, so we can't partial that out of our random error variance. Okay, so we've stepped up from univariate designs to bivariate designs, and in the coming weeks, we'll take a little bit more of a critical look at how we can interpret different kinds of interactions when we're dealing with multiple variables in our data set. Most of the time in psychology, we are dealing with multiple variables, so it's useful to develop a bit of an intuition for how to interpret interactions in your data. Okay, so now that we've come across a few p-values and our adventures of measuring differences between groups and correlations in our data, let's take a look at how we interpret them. What do they actually tell us? So in this section, we'll take a little bit more of a critical eye on the significance test and how we interpret p-values. So on that note, thinking about measuring differences and interpreting p-values, let's put some of this into practice when we meet for class next. So I'll see everyone in class.